Welcome, everyone. I'm Steve Hill, CEO of New Hydrogen. Joining our podcast today is Dr. Faisal M. Alamgir. He's a distinguished expert in the field of materials science and engineering. He's a professor of the School of Materials Science and Engineering and an initiative lead in the Institute of Materials at the Georgia Institute of Technology. Dr. Alamgir has dedicated his research to unraveling the incredible properties of graphene and its role in catalysts. He earned his BS degree in physics and mathematics, magna cum laude from Coe College, and later his PhD in materials science and engineering from Lehigh University. He's held various prestigious positions at institutions like Brookhaven National Laboratory and Hunter College of the City University of New York. During our conversation today, we'll dive into the world of graphene and its impact on catalysis, particularly in its use with green hydrogen production and fuel cell technologies. So without further ado, let's warmly welcome Dr. Faisal Alamgir to our podcast. Welcome, Faisal.
Thank you, Steve. It's a pleasure to be here.
I'm glad you're here. First, your work on graphene and catalysis has been extensive. Before we talk about it, though, can you briefly just explain about we're talking about catalysts and what are the limitations with catalysts today?
There are many limitations. It's a very active area of research, and catalysis is a process by which you essentially accelerate a chemical reaction. In the area that I work in, there could be another material, a catalyst, which is an active participant without being consumed by the reaction, and so it essentially offers a surface on which the reaction takes place, and the reactants, the chemicals, have to kind of chemically absorb on the surface, meet each other. Charge transfer sometimes takes place. The molecules shake hands, they react, and then they leave the surface. And so there's a lot going on the surface of that catalyst. That type of catalysis is called heterogeneous catalysis, and that's the area I'm in. And I'm interested in the catalyst reactant interactions, the fundamentals of that, how to design catalysts that fundamentally change the properties of the catalyst. Because once you make a catalyst and you put it to application, you can't put your hand in there and kind of change the catalyst again. It's baked in. And so we're thinking about the potential for kind of an active catalyst tuning and things like that. So that's kind of a quick preview of what the field of catalysis involves. Challenges on the area that I'm working with, or limitations of catalysts, as I already mentioned, one, which is that a catalyst properties become baked in once they're made and put to use, and so we would like to kind of be able to tune that, once it's in application. The second part is one other limitation is that the activity of the catalysis itself happens on the surface of the catalyst, and the surface of a material is just the outer atoms of that material, and so there's unused material on the inside, and that's holding up the surface, essentially the core versus the surface. So one way to kind of increase the activity, you might say, is to kind of smear out the catalyst in such a way that almost every atom is at the surface, or even pluck them apart and kind of make them individual atoms, in which case you'd have individual atomic catalysts. Now there's a whole area of burgeoning research called single atom catalysis. And so what I'm saying is that there's a way to kind of try and increase the surface area that is actively available for catalysis, but that comes usually at a cost. If you try to increase the activity by increasing the surface area, you necessarily, in many cases, also reduce the stability of the catalyst. The catalyst is then lost in different ways much more readily. So that activity stability dilemma is something that researchers are trying to overcome. It's a kind of a fundamental challenge.
Yeah, and I should say we're speaking of electrochemical catalysis here. And
I was speaking more generally. I was speaking about any type of heterogeneous catalysis,
okay.
but these challenges are, of course, there as well for electrocatalysis. Now, electrocatalysis means that you're doing a catalytic reaction, but the catalyst is also exchanging charge with the reactants, and so therefore you can drive it externally by power, or you can use the power that is being generated actively from that process.
So I was thinking about when you're describing that, is this kind of like, to help people visualize, is this kind of like you get a penny and it's all oxidized and brown on the outside? The inside of it's nice and shiny still. You could cut it in half and it would be nice and shiny inside. And so it doesn't have much surface area. So maybe if we took that penny and we flatten it out like a piece of aluminum foil or something, then you got more surface area, right? But it's super, super thin. And, maybe it won't be as stable as it's not going to be as strong as the little penny would be, of course. But that's kind of the idea, right? We want to increase that surface area that's exposed.
Yeah, penny is actually nowadays, just to continue with that analogy, it's a penny has got copper on the outside, but copper has become much more expensive over the years. And what has happened is that what used to be in the past a solid piece of copper has now become electroplated copper on a cheaper metal on the inside. And so basically, if the making a penny costs more than a penny, then it doesn't make sense. And so once copper became expensive enough, electroplating was used. And that's actually not a bad segue to one of the ways in which we are making catalysts, and we use electrodeposition, which is a form of electroplating to kind of generate our catalysts.
So how does this all play in then to your research and study of graphene? And what is it?
Yeah.
Maybe we just describe what graphene is first and then tie it in for us.
Sure. Graphene. So graphene is a naturally two-dimensional allotrope of carbon. And the closest family member to graphene would, in terms of another allotrope of carbon, would be graphite, which everyone's familiar with if you've ever used a lead pencil that's got the graphite tip. And so when you're writing with a graphite pencil, when you're writing with a pencil, you're essentially leaving graphene layers on your sheet as you're writing because they slide off the graphite. And so the structure of graphene is essentially a honeycomb structure of carbon atoms. So it's a two-dimensional crystal of carbon atoms. Now that two-dimensional crystal is separated from the next two-dimensional crystal in graphite and the next one after that, and that interaction between the layers is weak, and so a single layer can slide off quite easily. When you're writing, you're not just sliding off a single layer, you're smearing off probably many layers at a time of graphene. But what we work with are well-controlled numbers of layers of these graphene sheets. So we could work with a single layer, bilayer, and so forth. And the area of graphene research, or using graphene or studying graphene on its own terms, is also a big area of research. So, I could talk about each one of these things at length, but just to kind of speak about the salient points of graphene to our research, graphene for every carbon atom in the graphene has 3 covalent bonds, and that's a pretty large number of covalent bonds per atom for any atom to have in nature, and therefore if you were able to grab a sheet of graphene with tweezers and measure the kind of forces required to break those bonds or cause a tear in the graphene sheet, it would be fairly large. Now, obviously, it's not large for, if I was to pick it up or kind of handle a single sheet of graphene, it would still have to be supported on something because you wouldn't be able to just pick it up. It would break easily, but that's because I only have to make a break in a single atomic layer of material. Um, there's no real analog of this in other things that we handle in terms of mechanical properties. But if you translate that the forces that we would apply uh, to break those bonds to the macroscopic world, it's actually a very strong material. Okay, so it's a very strong material in the in plane direction, and out of plane, it can be. I mean, it's kind of a moot point because if it's a single layer, uh, depends on what you mean by an out of plane force. So graphene usually is sitting on top of something because it needs, like if you need a large area of graphene, let's say millimeters, or let's say a bit more realistically, you know, my, many micrometers of continuous graphene areas, then it needs to sit on something. So usually the support and the properties of the support um, are affecting the graphene in a sense slightly. I mean, the graphene is resting on it, but because it's an atomic material, uh, you now have an atom to atom level of distance between the support material and the graphene and the exposed surface on top. So this is why we are interested in graphene from the catalytic point of view, is because we want to be able to manipulate the properties of a metal catalyst that we will grow on top of graphene by exercising control from the support below. That is one of the new directions that we're interested in going. But to back up a bit, if we were able to take metals and grow them in such a way that they form kind of strong bonds with the graphene sheet as they are growing, then it would keep the metal from having to ball up into particles where the metal atoms would seek out other metal atoms and try to form metallic bonding and kind of stabilize that way. We would form a competition by forming covalent bonds in the out of plane direction, so that the metal doesn't ball up and instead spreads out and forms a sheet. So that is our strategy, and that's the reason why we first got into trying to make graphene as a support for growing catalytically relevant materials, metals in this case. And so we were successful in able to create a two-dimensional metal, which is unheard of in nature. Again, metals don't want to be two-dimensional because the metallic bonding that you would find in metals are kind of isotropic and equal in all directions, more or less. It's kind of radially symmetric type of bonds, and so you want to kind of have other metal atoms come and surround an available atom, and so it wants to kind of form polyhedral like structures and or basically eventually spherical structures. Yeah, so it'll want to form particles, in other words. Graphene, on the other hand, has covalent bonds, and covalent bonds are very directional, very precise geometry to them, and therefore in this particular case of graphene, it ends up being forming these 100 these 120 degree angle bonds, and three of them, so that gives you your 360-degree circle in a plane, and so you get the so-called sp2 hybridization of carbon. So we have this one material that is covalently bonded, the graphene, and then this other material that wants to be metallically bonded if left to its own devices. But now the way we are growing it, an atom at a time, or kind of few atoms at a time, forces them to form kind of covalent bonds with the graphene first, and then laterally form metallic bonds with the neighboring metal atoms. So eventually we get kind of an interesting material where we have the metal film, which is kind of metallic in the in-plane direction, but covalent out of plane. The properties are therefore anisotropic as well. We can actually see the imprint of the graphene's structure in terms of the properties on the surface of the metal. Just to give a quick example of that, graphene has, even though it's a hexagonal structure, if you look at it, you will notice that there's there's two. If you identify two orthogonal directions, you'll find that along one of the directions, the carbon-carbon bonds form kind of like a zigzag pattern, and in the other direction, it forms this kind of like a pattern that looks more like an armchair. So these are, in fact, the terms used: armchair direction and the zigzag direction. The zigzag direction and armchair direction properties of graphene are slightly different from one another, the electrical properties. And so what we find is that when we grow the metal on top of it, we actually have on the metal now that anisotropy of properties in these two different directions, which normally in a metal you don't have. So that's kind of another interesting side effect of growing these two-dimensional metals. So that's kind of the area that we went in to try and grow these, have an extremely high surface area catalyst. Every atom is available for catalysis, potentially. And perhaps because graphene is just a single atom sheet of material, from the other side, we could influence the properties of the metal that we grow on top. And just as an aside, let me just say that the reason we kind of wanted to make this two-dimensional metal at the first place was because there is a whole body of literature that about a decade and a half ago that started to kind of fill the space of academic journals, where people were very interested in making very small particles just so that they had catalyst particles, so that they had high surface area. But then and obviously you would see that you get a lot of per atom activity, that would increase. But it was very hard to kind of figure out the rationality or the causality between the size, the shape, and the active sites on the particles in those types of studies, because it's very hard to control the shape and size of particle ensembles through synthesis in such a way that you wouldn't always have a distribution of different things happening at the same time. So the interpretation of data, or trying to follow one person's work and try to replicate it and understand what you might want to change so that takes the functionality in a particular direction, was very hard, because there were no kind of design rules that really emerged from that. And part of the reason was that these three-dimensional particles at a very small size and a large distribution of shapes and size was very hard to kind of understand. And so we decided to start with the understanding, and therefore we wanted to get rid of the idea of a shape distribution. And so everything would be basically atomically flat, so it would all be films. So that's the shape that we were dictating. And the dimension would be governed by the number of layers of these metal films that we would grow if we were growing it layer by layer. And so we were trying to have that control first and understand how does the property evolve, catalytic property evolve as a function of the dimension and the structure. Yeah.
And you've had a couple of publications and research, well, probably more than a couple on this. So what are your conclusions? Like what has been kind of your findings, all this science happening, and we're trying to figure out how to make a better material. What's the conclusion? What's the takeaway from that?
There are several conclusions. If I was to look at the body of work that we have been doing, there are three things that I can point out. First, that we can actually, as we hypothesized, we can influence the property of the metal that we grow as a catalyst vis-a-vis its catalytic activity, and not just the activity, which means how fast is the reaction happening, but also at how much energy cost, that is the measured in terms of the chemical potential, or the how much, if we were trying to drive that reaction, how far would we have to push the external power source to make it happen. So that's kind of what you might call the driving potential. So the driving potential is one metric, and the activity would be how fast is the reaction happening. That's another metric. Those two things could be controlled by the type of material you have on the other side, as we expected. and there was there were kind of these computational works, toy models, you might say, of different how materials would behave if you were able to do such and such, and there was a whole body of work that had been created along the lines of, if you matched this metal as a core and this other metal as a surface or shell, then the surface metal, which is the one that directly interacts with the reactants, now has a property that not only is dictated by itself, but also by the type of atoms that are supporting. So these core shell structures, different kinds of geometries, some of them were being synthesized experimentally, and some of these things were being validated. These ideas that were coming from computation were being validated, but a lot of things were very hard to validate because of the problem that I mentioned before, the distribution of size and shape, and also the composition. You try to keep a single atom layer of one thing, separated on the surface from everything else on the inside. It's hard to do when a reaction is happening, and as a reaction is happening, the atoms themselves want to sometimes switch around, and so over the time of the reaction, you could actually change the architecture of that core shell, and so all of these things were becoming very difficult to interpret. But if we were able to maintain those architectures and kind of systematically prove that these computational predictions were in fact true, that would be a very, very nice thing. So one was could you actually have a physical barrier between that prevented the intermixing of the surface material from the core material? And so here graphene plays an important role. So that's point number two. So the first thing was that, yeah, we could influence the properties, and we actually, using graphene, we were able to put different types of materials as the support, and we were able to show that, in fact, yeah, you can control the properties. But also the graphene retains this core shell architecture because it prevents the atomic diffusion of these larger metals through the graphene. I mean, it still, through the defects of graphene and just thermally, by the fact that the carbon atoms are still vibrating, and larger atoms can squeeze through given high enough temperatures. The idea is statistical. Basically, how much of it is happening, that amount that is happening is reduced significantly if you have this two-dimensional kind of diffusion barrier material. So those are two things that immediately we were able to show. The third thing was that if you then put graphene on top as a capping layer on top of the catalyst that you've already grown as a two-dimensional film, now the question might be, could you run a reaction through the graphene? That is, the reactants no longer see the catalyst atoms directly, but they see the graphene that you've put on top first. But the question might be, is the metal's behavior still, protruding through the graphene in such a way that you could run the reaction from the graphene side from 2 points of view without sacrifice or any significant sacrifice to the activity of the catalyst? And secondly, why would you even do this? You would want to do this because you want to, again, prevent this catalyst metal from again, this graphene would act as a barrier, and so it would prevent it from physically being lost, right?
Yeah, just to interject really quickly, that to maybe help people understand, that material, that metal you're speaking of, is usually like platinum, right?
Yeah.
And so
it's
that's an expensive metal. It's baked in, as you said before. Once it's spent, it's spent. And so when you're talking about the whole process, you want to preserve that as long as possible. Keep your activity high, low energy input, get the maximum out, and make it last as long as we can.
Right. Yeah. So as I alluded to before, the catalyst metals, often you have this activity stability dilemma, and in the case of these particular reactions under harsh conditions, the stability of the activity is very high for kind of these late transition metals, which are also often very expensive, like iridium, platinum, palladium. But because they're late transition metals, they're also a bit more stable chemically against oxidation and so forth. I mean, I'm brushing over things a bit too quickly and not pointing out a lot of nuances. But yeah, just relative to, let's say, a nickel or an iron, platinum is a lot more chemically stable. And you want the catalyst not to be too active chemically, because you don't want it to participate in the reaction. You want it to be there, helping the reaction happen on its surface without being consumed. Remember that's the whole idea. So it turns out that, yeah, these are usually precious metals, and so very expensive. So you don't want to lose them. And so having graphene there, another hypothesis we had was that if it is true that we can affect the catalytic properties from below, then if we put the graphene on top, then we should be able to have the properties permeate through as well. And in fact, that is what we found. And so we did a side-by-side comparison for a canonical reaction for a fuel cell. It's called the oxygen reduction reaction, and there, over 1,000 cycles with and without this graphene cap, we found that we lost about 40% of the activity for the case where we didn't have the graphene cap, and with the graphene cap, we didn't notice any loss. Not any. I mean, within error, basically, we didn't see any loss. So this is a very important result, and it's something that one can use for designing new stable catalysts for the future.
Awesome. So I mean, it's a technology that I think that's kind of, so this is the extra layer there, right, of graphene on the exterior. Right. What you're saying is that was able to protect that right. The base material so that it didn't oxidize.
Yeah.
It's fascinating.
Yeah. I just want to add another point about this. That we have a publication that's coming. It's been accepted and it's already available online. And it's a third case now where we're kind of making ravioli-like structures with platinum in between graphene sheets. And although these are not kind of free, pieces of ravioli that are kind of floating around and you can just pick them up and use as will. Yeah, that's the idea for the technology development side. But we wanted to first show that concept works, and we were able to kind of show that does indeed work. So that's another thing that's just come out. So we have the trapped graphene between layers of trapped platinum between layers of graphene that allow you to run reactions for 30,000 cycles without significant loss.
Incredible statistics. And I know we're out of time, but I want you to be able to have a chance to say two more things really quickly. One is, and I know this is going to be tough to do in a short period of time, but other applications for this material. And then maybe a little bit about your department. Anything else you want to say?
Yeah, I know that your company is focused on the hydrogen economy, and so let me just say how my work is connected to hydrogen. So one of the reactions I mentioned already is the oxygen reduction reaction, and that is part of the reactions that is used in a fuel cell. If you're interested in how a fuel cell works, there's plenty of YouTube videos or text online, or there's a lot of resources for figuring that out. But just to say quickly, a fuel cell essentially relies on catalysis that's happening on both the cathode and the anode side of the device, and it's usually the same catalyst on both sides, and it's platinum still is the best one for fuel cells, although for different types of fuel cells, there may be some other ones that are better. For example, high temperature fuel cells can work with nickel. Okay, so the idea of this catalysis and how to have better catalysts and how to protect the catalyst, all of that stuff works for fuel cells, which are a part of the hydrogen economy. So a fuel cell uses hydrogen on one end and oxygen from the other, from the air from the other end, and essentially breaks those molecules apart and has them react within the device to produce water. And in the external circuit, you have a charge flow. So if you're going to use hydrogen in a clean way, if we can produce hydrogen in a clean way, you want to use hydrogen then at the user end in a very clean way, so that that use of hydrogen doesn't produce carbon dioxide or any other kind of greenhouse gas. And in this case, that's what the fuel cell would do. So we are working on the hydrogen utilization reactions side, and we are also working again from catalytic point of view from the hydrogen storage side, or one can argue it is for hydrogen storage, in that hydrogen is a gas and wants to be a gas, and so if you want to transport it, you can either pressurize it to increase the concentration of per volume, and eventually liquefy it and so forth. But that itself takes a lot of energy, and so it would be better to kind of chemically liquefy. That is, you were to take the hydrogen and react it in some way, in a way that it forms a room temperature liquid, and then we could transport that liquid much more efficiently. And then at the user end, have one extra step to the utilization. The fuel cell would have to then break that molecule up to hydrogen first, and then react the hydrogen. And so one of the reactions that we're looking at is this formation of what's called formic acid, by taking carbon dioxide and reacting it with hydrogen from water. And so in another sense, that formic acid is also trapping the CO2 molecule while the hydrogen is being stored. So that's another aspect. So that's more on the kind of transport and storage of hydrogen side. And I'm in the Department of Material Science and Engineering. I'm a professor here at Georgia Institute of Technology. We're in the heart of Atlanta. And so, yeah, if you would like to visit my lab or just visit Georgia Tech in general, you can get in touch with me, and or you could just also just email me to have a chat. And yeah, I have a research group. I've been active in research now for about 15 plus years at Georgia Tech. So I look forward to bright students applying to my group in the future as well. And so, yeah, please get in touch.
Fantastic. Definitely, if they want a comprehensive learning experience with a well-seasoned and obviously passionate professor, there's no better place to go. Dr. Faisal, thank you so much, Dr. Alamgir, I should say. Thank you so much for joining us today. For those of you who are watching, who are interested about how all this ties in together with new hydrogen and our production of the world's cheapest green hydrogen, we hope, check us out at newhydrogen.com. And thanks everyone for watching today. Hope you have a great day. And thank you, Faisal, again for joining us.
Thank you, Steve. Really enjoyed it.